Fabulous. G'day. The TLDR of this talk is that we shipped a game on Windows and Mac OS with Rust and Vulkan in about 100 days. Most of the things that we did worked great. Some of them didn't. And I'm not going to try and force you to use Rust, like heads up, okay? You should try it if you want to. But just to indulge me, please, quick show of hands if you've written a single line of Rust, like hello world. Yeah, cool. Put them down. Not yet. When I say so, please put them down if you haven't written anything substantial. Okay, so, and then lastly, if you've used Rust and Vulkan together. Excellent. One of us, one of us. All right. So as a high level, I'm going to tell you why we picked Rust and Vulkan, how we used them, the things that went well, and again, the things that didn't. For a little bit of context, this is me with my favorite sponsor render. I'm new to graphics compared to a lot of you. I've been using Vulkan for 5 years now. It's the first graphics API I learned. But before that, I had about 15 years in like low-level networking. And so to me, networking graphics are kind of the same if you squint. Data comes in, data comes out, you do some stuff in the middle, and you call it a day. I run a small indie studio in Melbourne, Australia. We started out with mobile VR, so really, really perf-focused on the Quest 2 for those first titles. We use Rust for all the things. We have our own engine. Team of 5 are the contractors and 1 graphics engineer. But as you know, indie games are a very stable and lucrative revenue stream. My wife is really happy about that. And so co-development pays the bills. You know, that's just the reality of the gig. And so I really want to make it clear that the thing we're talking about here is something where an external third party, another game studio, approached us actually for our Rust and graphics expertise. They'd written something in Rust, but just didn't have the core graphics expertise in-house. But it was very clear when we got onto it that the project itself was really in a death spiral. They needed so much more than graphics. And so after a quick bit of negotiation, we decided to take over the project ourselves, which turned out to be a real win for us because honestly, it made us a lot of money and put a bit of runway there, but also really gave us an opportunity to flex our skills and get our name out there. So in the end, we ended up rewriting 99% of the code that we were given. So the thing that we were building was a Minecraft 1.8 compatible client. The things that we kept was like the protocol layer stuff, all the chunking code. I'll explain what that means in a bit. But really everything else was from scratch. And we needed to ship to beta in 3 months was the deadline that we were given. And you know, we were remunerated accordingly. And you know, how hard could it be? Come on, I mean, we're all programmers. 3 months is our magical estimate for everything, right? And you know, for me, like, I look at this and I'm like, oh, this is like 2009 stuff. Like I'm used to doing like PBR and a tiny little Quest 2 with like dynamic lighting and stuff. This is just simple. This will be an absolute piece of cake. I mean, it's pretty simple. You just have these voxels. They're 1 meter by 1 meter. I mean, there's a lot of them. You know, it's about 120,000 Ks across. I mean, yes, it is a shared dynamic multiplayer world. And yes, every texture and resource can be replaced at any time. And yes, there is sort of like dynamic voxel. Yeah, okay. All right. It turned out to be a little bit more complicated than we thought. So, but first, I want to start with why we chose this combination of tools. So the sort of default impression that everyone has with Rust is it's kind of a buzzkill. It doesn't feel like a sexy language. It's kind of like it's like your mom that's trying to tell you like, you know, wear your jumper and don't get a cold and stuff like that. But this is not, I think, a super accurate perception. In fact, I think the best person to answer this question is if anyone was at GPC last year, you would have seen this presentation from the team at Tiny Glade, which this should be at the top of the Vulkan showcase list. This game is just absolutely incredible. But predictably, after giving a talk on a game that used Rust, the graphics engineer, Tom, was asked that same question. And I think he answered it way better than I could have. And I tried to bully him into coming here and he didn't. So you have to listen to me instead. But essentially in 2 years of development, they didn't encounter a single memory corruption bug. And I think that's something that's worth noting. Because if all you ever do is write safe Rust, you will never, ever have to worry about memory safety. You will never get a dangling pointer. You will never get use after free. And you'll never get any kind of UB. And Shannon, as we all know, with undefined behavior, anything is possible. So if I have sufficiently convinced you that this is a good idea, you might be wondering how. This for the most part, is a talk where I'm just telling you anecdotes of what I've done, but this is the only bit where I'm going to give you a really strong opinion. It is trying to extend Rust's safety model to the GPU is a profoundly terrible idea. So many Rust developers look at Vulkan and go, it's a big pile of C. There's undefined behavior on the GPU. And so what they end up doing is very poorly implementing the validation layers as a bunch of asserts in their code. And this is you're just ruining, why are you using Vulkan at that point? The whole point of Vulkan is that we have an explicit API that we do the right thing and we follow the spec. Now, there's an asterisk here, of course. If you're web GPU and you're running untrusted code, fine, I get it. Very reasonable decision. But for the most part, don't do this. This is just not the way to go. Because the thing is, while that memory safety is very useful for most of the code that we write, Rust does let us opt out of its safety guarantees. There's a thing called unsafe Rust. And it's kind of a bit like going, hey, Rust, let me cook. We're going to do some pointer arithmetic. We're going to do some wild stuff. Close your eyes. And so the way that the primary way of working with Vulkan and Rust is a package called Ash. And if you kind of squint, it looks pretty similar to Vulkan HPP if anyone's used that. Here, what we're doing is something very similar to what you would see with Vulk or VK Bootstrap. We're loading all the function pointers from the driver into a thing called an entry. And then we create our instance. Again, it's just Vulkan. And the benefit of using a wrapper that is similar to the C API is that I can look at the spec and maybe if I've had a glass of wine or two, they kind of look the same, right? It's not some completely bespoke API that's doing weird stuff. And the thing is, the validation layers are there for a reason, right? I shouldn't be having to try and do all these insane things in my wrapper because Spencer will do them for me. So our first challenge. So just quick bit of detail. I had never even played Minecraft before, so I had to speak to a lot of people's 13-year-old kids to kind of understand what it was. One of those how do you do fellow kids moments. So basically the world is split into these chunks. You've got 16 by 16 on the X Z plane, 256 high. And so obviously the first thing that I did was downloaded the world off the server and just wrote a for loop. This ended up being 1.84 million draw calls per frame. And so, I was like, look, we'll get something on screen and the driver will probably hang and we're not going to get interactive frame rate. 60 frames a second on my 3060 Ti. NVIDIA, your hardware is unreasonable. Stop it. This shouldn't be possible. So challenge number 2 was to do this in a non-insane way. And so the normal approach to this, if you've ever done this sort of thing, is you do this thing called voxel meshing, where you have these very sophisticated algorithms where no time for that. Okay, we got to ship this thing in 3 months. We are not going to try and do anything fancy like that. Instead, what we're going to do is we're going to build a buffer of faces per chunk. What we're going to do is we're going to issue a draw call where we take the number of faces that are in that buffer, e.g. the ones that aren't air, multiplied by 6, you're going to see this 6 number a bit. In our vertex shader, we take the vertex index, divide that by 6. If you've done this trick before, you can see where I'm going. And that lets us extract from our face buffer the data, like the material or whatever other information we need for that particular face. And then we can just index into a constant array of vertex positions to get the local space of that. And so very neatly, we get 6, 6, 6. And so this worked quite well. I just did a thing where I just stored a random color value in the buffer just to prove that we could read everything out. And this proved to be a very, very simple solution. I was able to stand all this stuff up in really a handful of days. As an aside, so you'll notice I'm saying face and not cube. Remember, this whole conference is about lies. So Minecraft doesn't really think about cubes. Instead, it has this really crazy JSON format that does inheritance and all these other evil things. But essentially the way it works is you have a list of elements, which are sort of AABBs, you define the extents of them, and you have a bunch of textures. And so obviously people do stupid things like create incredibly complex things out of this. What I did was I made a model with my face on it to punish anybody that didn't load an asset correctly. I really wanted to ship this into production, but they took it away at the last minute. I thought that would have been hilarious. And so once we had all that stuff going, the challenge was then getting it running on something other than my very nice NVIDIA machine. So we knew we had very limited time. So when the client approached us, we just told them straight up, we are not going to deal with old or integrated cards or any of that sort of crap. We're just going to try and target more modern things. Like if we're going to move quickly, we need to use modern features and we needed to just trust that the drivers were going to work. And so we're able to negotiate a min spec of like a GTX 1060 or the AMD equivalent. Interestingly, for this customer, almost 30% of their players are on Mac. So we just said the M1 Pro was there. So the sort of feature set that we settled on was the one thing that I really wanted to push for was buffer device address. We just kind of used like a single all the textures descriptor set. I'll cover this in a little bit more, but we kind of worried that some of these things were a little bit newer in Molten VK, and so we kind of played it safe. We didn't use things like dynamic rendering. We didn't use Sync 2, and this was a mistake. This was overly conservative. I will get into that a little bit more. So, okay, so once we've got that sort of feature set going, we've got to render some other stuff. So in Minecraft, entities are anything that's like not a block. They can move, animate, hold other entities, all that sort of stuff. We use GLTF and all of our other things, and so we ended up doing the same here. We wrote an exporter where we could go from that crazy Minecraft model format and just ingest GLTF. We did that with, we just have like a single vertex index buffer where we import all the geometry, plus we've got that just all the textures giant descriptor set that we could use. And then what we do is we store offsets per model into that giant buffer, and then record texture IDs every time we see a new texture. And this worked incredibly well. Like this continues to just be a very unreasonably effective strategy for rendering GLTFs. So in Minecraft, light is very important, not just for the visuals, but also there's gameplay stuff as well. And one of the crazy things about this game is that lights can be placed and removed arbitrarily at any time by players. There's also things like caves and tunnels and pits because players can dig and go underground and put a door above themselves, and that needs to be instantly reactive. So this is all done with a flood fill algorithm. And so what we would do is store the light value per block in a buffer, and then update that data when the chunk gets modified, and then just fetch the light value in the shader. And this turned out to be very effective. And so honestly, in probably about 2 or so months, we were able to get all the things rendering on the screen and getting everything going. And we were very pleased with this. So the problem, though, is that we did a bunch of crimes. And, you know, when you're moving quickly, you know, you start to build your crimes list, and eventually you trip over the pile of cans that you've been kicking down the road on the project. So sync, as you can probably imagine, with all this data being updated constantly and everything being totally dynamic, it quickly emerged as a major issue that we needed to sort out. Because again, any resource can be updated at any time. Also, the server can just decide, hey, all of these blocks have a new texture now, and you just have to deal with it. Any model, any block, everything can just be randomly updated. And so I made a really strong decision that I wanted to focus on correctness first. I really had the confidence that we could punt on the performance, that we could just wait to get to the end and fix these things up, because it allowed us to show the client that we were making progress and that we were getting things going. But what this meant was we used the big dumb sledgehammer. I say we, this is me. I can't blame anyone else here. I used it in all buffer and image operations. Render paths was just they were an absolute mess, and we'd had predictably terrible performance. Don't do this. I really want to make this clear. I am not saying this is a good thing to do. This was a decision that we made under the conditions that we were working with. But wait, there's more crimes. If you're in this audience, you've probably either seen this image or probably made it yourself. We were all the way over here doing the worst possible memory management. We were allocating and freeing every frame. As we started adding more and more data to those face buffers, this was looking like 1.2 gig worth of data. These started as hitches and then started to end up as driver hangs. Turns out if you do enough dumb stuff, you can kill an NVIDIA driver. And we were still working on features with 1 week to ship. Like this did start to cut a bit fine. And it was very clear to me that I just need to burn all this stuff down and start again. So when you are faced with a challenge like this, there is only one solution. Does anyone know what this is? Ivan? This is kopi openg. This is a coffee drink that's found in Malaysia and Singapore. It is basically just condensed rocket fuel, essentially. It is so thick, it is so spiced, it is just beautiful, and it comes in a plastic bag and costs 20 cents. With kopi openg, all things are possible. And so my beloved wife would basically come into the little room that I locked myself in and hang up a bag like it was an IV drip. Which, and then feed me these beautiful, fried durian things, which probably also contributed to the severe stress I was putting under my heart with all the coffee. And so fueled with this incredible power, removed all the usage of device wait idle, switched to dynamic rendering, and then just ran sync-val and just waited for it to scream at me. Did the right things, I did what it told me to do, and everything worked out great. So for our memory strategy, we just, once we were very confident that we knew the size of our data and how many chunks it would have on the screen at any time, it just became trivial to allocate all the data that we would ever need on init in device local, sub-allocate into that with offsets. Shout out to Seb's offset allocator, which is just, again, unreasonably effective. We had the traditional approach. We had a scratch buffer for transfers with a queue if that ever got overflowed. And then what we would do is in our shaders is we would grab the base address of that giant all the memory buffer and just offset into that. And again, everything worked out great. We shipped it and it worked. We got it done in the time that was required. We added some instrumentation to catch driver bugs. Our own bugs. We ended up the only bug that we ended up happening was that there was some older devices that that didn't support a feature that we really didn't need, and then fix that. So, in my opinion, I think this is a real win. So I want to recap some of the things we did. So the good things is that Rust let us move quickly. Even though it's not as relevant on my side with the graphics stuff, the fact that the gameplay programming guys people just didn't have to worry about that stuff at all is very good. And we don't have to deal with SameMake. It's pretty good. And a simple bindless renderer allowed us to just reuse these similar patterns across everything that we were doing. Buffer device address is the cat's pajamas. It just is so good. I really can't stress enough, if you're not using it already, go home and do it now. And the main point that I want to make here is that Vulkan gave us the confidence to come back and fix the crimes later. That isn't something that you can say with every bit of software. As it did get a little bit stressful towards the end, but I knew that it was possible to do it correctly, and I knew that the tooling would be there to support it, and that gave me the confidence. And then lastly, Molten VK is great. It just works. We have shipped it and we were doing some very interesting things and we just didn't have a single issue. If you want to get your game running on Mac, use it. And so just my eternal gratitude to all of us. I think we all owe RenderDoc a big thanks, but also just the entire team working on debug utils. Like, these things are just so unreasonably good. Validation layers, we were using debug utils. And what that allowed us to do was it meant that if there was a bug, if there was a graphics crash, it meant that people who aren't graphics programmers, who aren't experts in Vulkan, could create issues with meaningful and actionable information. It was a requirement of every developer that they be running the validation layers at all times so that we could catch anything that I was doing wrong. And again, just the incredible documentation, the spec, the sync examples, and also a special shout out to the TU Vienna lecture series that just had an absolutely amazing explanation of sync that I finally got around to. The things that we did wrong, really should have been less conservative about those modern features, but as with anything, and probably should have thought more about the amount of data that was going to be changed and should have realized a little bit early on that this was mostly going to be a sync problem. So again, in summary, we shipped a Vulkan game with Rust and Windows on Mac OS. Some things were good, some things weren't. And if you want to try Rust, you should. Thanks.
Hi, lovely talk.
Cheers.
Are you suggesting as a realistic development strategy is to not try to synchronize anything and just at some point decide, okay, remove all the device-weight idles and let SyncVal tell you what's wrong and not think about it any further than that?
No. I wanted to give you a bit of pause, just to put a bit of terror into your heart. No. This, like I said, we had guns to our heads to make this work, and that was just, I'm the boss, I get to do whatever I want. That was a decision that I made. Would I do this again with a different product? Honestly, I can't say. I think that I think I definitely learned how much easier it is to do it the right way, honestly. And that would have, I think that I might approach a thing like this differently next time. But yes, I definitely wouldn't say that this is a mainstream development strategy, no.
Somebody had a question?
So I had 3 questions. One being
Fantastic.
Yeah, fantastic. So one being, what windowing and GUI technology do you use?
If we can just go one at a time, I've got a very short memory.
Okay.
So we used, just in case anyone doesn't know, Rust packages are called crates for reasons that I don't know. So we used Winit for everything, and that was just fine. Yeah.
And then the second question is, how much of your code base was marked as unsafe?
The only unsafe we used was for the Vulkan calls that were unsafe. The only case where there was actual unsafe needed was things like, you know, taking like Rust structs and then blasting them into our scratch buffers. Like, that's just going to be unsafe always. The borrow checker can make no guarantees about that stuff. But yes, unsafe was just minimized to graphics code.
And then the third question is, did you run into any compile time like bottlenecks in your iteration of development? Or
Yeah, so I was very fortunate enough to be able to get a M3 Max for development on this, and that was pretty cool. So we could do a cold compile of the entire project in about less than a minute on the M3 Max. Yeah. Yeah, thanks for the questions. It's really good.
Hi, I'd like to congratulate you on the talk. I think you did everything correctly. Buffer device address, description, indexing, fantastic. So instead, I'm going to be very mean and unfair to reward you for that. And I'm going to ask, why was that shader code clearly not Rust? Why did you not Rust? You use Rust GPU. It's actually being worked on.
Yeah,
it's not dead, if anyone is wondering.
Yeah, there's 2 answers I can give you. There's an answer that would like benefit just you, like anyone who's like nerdy about that. So I'm not going to waste everyone's time with that answer. But the simple answer is just it wasn't mature enough. We did start, again, this was us being overly conservative. We did start off with GLSL, but as I said, in November last year, when we've still continued to work on this project in the meantime, we converted everything to Slang and had a fantastic time.
Thank you.
No stress.
Yep, thank you for the talk. I have a bit of a Rust specific question, probably.
Sure.
Do you do anything above Ash to handle properly resource acquisition and freeing in conjunction with the question mark operator? Because like you showed. Showed on a slide, yeah. For the initiated question mark operator is like a cheeky early return on error.
Yeah.
And one thing that I find really big pain is like if you create more than one resource in a function and use question mark operator, you need to remember to free it or either have it like wrapped into something or something.
I'm not quite sure I understand the question, but maybe I can just flip this back to you as an answer. What happens is that the way that Ash works is similar to VK Bootstrap or anything else that's wrapping the Vulkan API. It just returns a result struct. right? Like a result enum rather. And just question mark is a way of propagating that result upwards.
No. I know that. The question is, if you created a resource,
What do you mean by resource? Sorry.
I don't know, buffer, image, whatever else.
Yep.
And then you create something else and it fails and you early return, the resource that you create successfully previously leaks.
The resource that you created previously leaks. I mean, yes, that's because the Vulkan API.
Do you do something with that?
No, and this is what I'm saying is that we did not try to create any clever RAII stuff at all. I think that's just an absolute trap, especially with Rust, because as I said, Rust's drop semantics are very different, and so all of our cleanup code for our resources, etc., we just use the Vulkan API to do that. Functions and structures, that's what we did all the way down.
Any other questions? In which case, let's thank our speaker.